Thank you. Okay. Hi, everyone. So I'm aware that I am the only thing, so I'm in a dangerous position here because I know I'm the only thing that stands between you and lunch. In fact, I'm the only thing that stands between everyone here and the end of the wonderful workshop. So I promise I will try and be efficient, and there will also not be any proofs in this thing. So my goal is to try to be as expository as possible. So my title says that it suggests that the talk will be about reducibilities. In fact, when preparing for this talk, I wanted to be ambitious, right? I wanted to discuss all the different exotic reducibilities that may have appeared in computability that people may not know about. But I will limit the scope to just a few. So yes, so a large part of the of what I am interested in is to really examine how computation or algorithms interacts with different concepts, right? And I think this is one of the main thrusts of computability. In particular, we want to examine the complexity of different objects and constructions that we use in mathematics, putting on the idea of examining them through perhaps algorithmic considerations, right? And the question is, how would you classify, or how would you even begin to describe this complexity from the algorithmic point of view? And it is somehow this question through the idea of measuring this concept through the idea of relative computational strength. Right, this is where we want to look at reducibilities. Now, the most common way, of course, of doing this is through the use of the Turing reducibility. So now, the Turing reducibility is perfect, right? If you are thinking of calibrating or trying to understand, right? If I give you two pieces of information, if you're trying to understand or trying to compare the algorithmic content of these two pieces of information, if you were interested in measuring the algorithmic content from the point of view of a decision procedure, right? If you're thinking that, oh, this thing is complicated, if it is difficult to decide information about this object, then the Turing reducibility is, of course, perfect. However, there are different situations where we may not want to view things this way. So sometimes we may want to change the model of relative computation, and let's say M is just any such model of computation in whatever domain. Then the usual thing is we say A is M reducible to B, B being larger stands for the fact that B is more complicated or should have more information as measured by the computational model M compared to A. Okay, as usual, this induces a degree structure which we call the M degrees. So just an example, I think many people here know. If you were interested, right? If you're trying to understand positive information about a set, right? If I give you an information, if I give you an object and you don't really care about deciding elements of this set, but you really only care about the elements being enumerated at some stage, then the enumeration reducibility captures exactly this notion of relative computational strength. It allows positive information about one set to produce positive information about the other set. So example is if you have any set of vertices in a computable graph, then the set of its neighbors would be enumeration reducible to the set, right? If you didn't care about computing the elements of F or its neighbors, you only care about eventually you see the elements, then this perfectly describes the situation. And therefore, if you have a maximal independent set of vertices S in the computable graph, then then the complement of S it can be enumerated from S. Okay, in general, this is not true unless S itself already has an enumeration without any oracle. Okay, so I guess in this talk I'm going to try to consider what different kinds of computation, different models of computation, different arising degree structures, and try to study them. Of course, apart from the intrinsic motivations, right? I think it's interesting to kind of study how these different degree structures arising from different models, especially in connection with the Turing degrees, which is of course the most well understood, the most well studied degree structure in computability. But I think it's also kind of, through comparing different degree structure, is kind of also interesting because it allows us to understand how the different models of computation are different from each other. Hopefully, through these comparisons, allow us to kind of shed light on these different kinds of computation, and also these are also chosen so that there are these different reducibilities are kind of arising naturally in these different areas. Okay, so the first thing that I'm going to mention is right. So there's been like a large series of talks in this workshop on descriptive set theory and higher recursion theory. What I want to kind of focus on, at least in this part, is perhaps what you might call lower recursion theory, right? So we want to go the other extreme and try to understand things which are below that of computability. So at least for this part, right, I'm going to try to go a little bit more dynamic. Okay, so I think the basic motivation comes from this class of problems called online algorithms, which have been studied in computer science. This is for finite problems, finite structures and finite problems. And the basic idea is this, right? You have a finite piece of information, and your job, like a graph or something, right? And your job is to solve for certain aspects of this thing, right? You want to find matching or something. And if you think about it, there's two kind of situations in which you might be called upon to perform this task, right? First of all, there is the situation where you have to make the decision online, right? So bits of the input arise one at a time, and as bits arrive, you have to kind of give your decision about each bit, more or less immediately, without seeing the whole of the input. Versus the offline situation where you're allowed to defer your decisions until you see the entirety of the input, and then you make decisions collectively about everything. Yes. So obviously, it should be quite clear that the offline situation presents a significant advantage, right? Because once you see the whole large but finite piece of thing, then of course you could make the most optimal solution. Whereas online obviously puts and so people have to try to get creative in the online situation, appeal to probabilistic algorithms, blah blah blah. So there's a huge study of this kind of thing. And so I think the idea is kind of to think about what this means in computability, right? If you have an infinite piece of information, what does online or offline mean? Now, first of all, just a quick remark. If we are thinking about computability on an infinite object, generally seeing a finite piece of that is generally not enough. In general. In fact, this kind of feature, right, where a finite piece determines nothing of the rest, is often exploited in familiar arguments such as diagonalization, forcing arguments, and so on and so forth. So finite generally is not going to be enough, but here is just another toy example. If you have a computable infinite tree, not a forest but a tree, then that has a computable two coloring. This is quite obvious. But How would you do this, right? If you think about this, if I give you, so if you think of the tree, if you think of the vertices of the tree as being presented one bit at a time, then as vertices arrive, you want to try to color each vertex. You know the whole tree is infinite, of course. But to do it, you actually don't need, right? So what does offline mean in this case, right? If you are trying to make a decision about a particular vertex, you don't need to see the entirety of the whole tree to make decisions about a fixed vertex. Right? All you need is a sufficiently large, finite part of the tree to show itself, and then you know how to do it, right? So in this particular case, you just wait for the vertex in question to be connected to the root, some fixed vertex you make, and then you can consistently color everybody else. So this is what we can think of as an offline case. So it's a recognition that for infinite computations, you can sometimes still talk about offline, if you're requiring only a finite piece. But it's pretty clear in any case that this task cannot be achieved in an online way, right? Because if a vertex comes and you have to immediately assign a color to it without knowing its relationship with everybody else, or at least with a root, then there's in general no way to do it. Okay, so this example I think is kind of illuminating. It tells us how we can best think about offline versus online in the same vein as what we had for the finite case. So in this particular case, offline represents the ability to wait perhaps unboundedly long. Finite, right? It's a finite wait, but there's some kind of delay. So to forbid this, we simply just prevent the unbounded search. Now, of course, one other way that you might want to try to put a restriction on online versus offline would be to look at complexity classes. And in fact, there have been a large body of work done in the 80s on different kinds of polynomial time computable, mostly algebras. And there's many results in the literature. Indeed, for some classes, for many classes, every computable structure has a polynomial time copy, for example, in linear orders, some kinds of Boolean algebras, and so on. Unfortunately, in this particular case, we would prefer not to do this because, well, first of all, if you're looking at complexity classes, this is somehow more sensitive. It's a little bit too sensitive because, for example, it's going to depend on how the domain is presented. So we don't want to always just split our results into two parts. And also, if you allow complexity bounds, then you're going to consider a whole hierarchy of notions of being online, and we don't really want to do that, right? So we want to be a little bit more generous. And here the model is that we adopt is just being based on using a primitive recursive algorithm. So that's the first model of computation we're going to look at. Here, of course, there are some nice properties, right? If you look at primitive recursive algorithms here, for instance, there is a computable enumeration, right? So first of all, the cleanest T predicate is primitive recursive. So this is a big step because this allows us to enumerate all primitive recursive functions in a computable way. You have closure under composition and primitive recursion, which are the two operations that we will use most of the time. And there is also this restricted Church's thesis, which basically says that any algorithm has a primitive recursive implementation if you can describe a pseudocode, right? If you can write a pseudocode for it that doesn't use the while loop, so you're allowed to use for loop as long as you specify how many times to repeat the loop. And so there is a long history, but just to cut it short, following Maltsev and Yershoff, this following definition is to call a structure to be primitive recursive or punctual if the domain is omega and all operations and relations are uniformly primitive recursive. So I just want to point out that it's important here that the domain is omega rather than just a primitive recursive subset of omega, because that gives rise to a slightly different notion. Okay, right. So with this model of computation, you can kind of do many things, right? So I'm just going to talk about one particular class of problems. So the idea comes from the notion of of a computable structure. In computable structure theory, there are people try to understand the computational content of certain structures, and one of the ways in which one can try to understand or measure the content of a structure is by looking at the minimal complexity. Is to see how is to try to calibrate how difficult it is to compute isomorphisms between computable copies of the structure. And here, well, there is the obvious definition. We call a punctual structure to be punctually categorical if whenever I give you two punctual copies of the structure, then there is a primitive recursive isomorphism or punctual isomorphism. Now we need to be a little bit careful about what a primitive recursive isomorphism here means, for the obvious reason that the inverse of a primitive recursive bijection is not necessarily primitive recursive. So it's best to just state it in this way, right? Okay, so there are a couple of different definitions we could make, and I think this one here kind of makes the most sense because it coincides exactly with being able to carry out an online back and forth between two punctual copies, right? So that should be, in essence, the correct definition of a structure to be being punctually categorical. If you give you two nice copies, then you can go back and forth, matching elements in an online way. So you need to talk about both F and F inverse being primitive recursive. Okay, so just as an example, if you look at the additive group of infinitely many copies of ZP, you can think of this as an infinite dimensional vector space over a finite field. This is functionally categorical because if I give you two copies of this group, then you could efficiently match up elements in one with the other, because the only thing you need to know is whether the next element is linearly dependent over the finitely many elements from before, and this decision can be made efficiently because field is bounded, right? There are only p many coefficients, so there is no need for an unbounded search, right? You know exactly how many steps you take to figure out whether the next element is independent over the previous ones. So online back and forth in this case works. However, if we take the next thing which normally we would associate to be simple, the countable dense linear order without endpoints, that turns out to be not punctually categorical, right? Even though just usually we would normally think of this as the standard example to teach a back and forth argument. Well, here basically the idea is that the problem is here that the language is relational. So the problem is that the sigma 1 Skolem function is not in a language, so it's not necessarily efficient, right? So you could have elements appearing in between, but then in the other copy maybe there's no such thing appearing quickly, and so an online back and forth does not work. You need to search or wait unboundedly before you can do the back and forth. Okay, so I've mentioned some notions of here are some possible candidates for an online or a punctual isomorphism. The first one was kind of what we have discussed. You could also talk about having an isomorphism where the graph is primitive recursive, or you can talk about having a primitive recursive isomorphism from A to B and a different one from B to A. Now, classically, for computable isomorphism, these are all equivalent, but these three are all different in the primitive recursive case. Okay, so we're going to try to make the definition a little bit more general, right? So if you have two functional structures of the same, two functional copies A and B of the same structure, then we can say A is reducible to B, or PR reducible to B. If you can find a primitive recursive isomorphism from A onto B, and this gives rise to a reducibility, and we let PRA denote the arising degree structure under this reducibility. Okay, so the idea here is that again, right? If we think about what this means in terms of comparing the information, then A being reducible to B kind of measures how quickly the copy A is compared to the copy B, and if A is reducible to B, that kind of means that every time you have some finite piece of A appearing, then by the time it appears in A, the corresponding pieces would have appeared in B. Right? So that kind of means that B grows faster than A, or B grows no slower than A. So example is if you take a standard copy of the rationals, the dense linear order reliant points, that is the greatest element in its degree structure, because any other copy can be embedded inside there quickly, because in the standard copy the E Scollon function is efficient. And we look at the standard copy of the natural numbers with successor meaning the function that generates the next element, then that is the least element of its degree structure. Okay, so now we have this degree structure. Suppose that of course we can kind of try to understand what some of the questions are in each of these structures. So the first thing is that for graphs, it turns out that a graph is punctually categorical if and only if the PR degree structure of G is 1. So remember what this means. Having a single PR degree means that given any two copies of G, you can find a primitive recursive isomorphism going one way and a different one going back, right? And that turns out is equivalent to having F and F inverse, both being primitive recursive. If you have a graph or a unary function structure, then the PR degree structure is either 1, size 1, or infinity. This is kind of the analog of the of computable dimension n. So it turns out that for every finite n, this is finite n, there is a punctual structure of punctual dimension n, and in fact the PR degree structure also has exactly n degrees, and also we can also show that every punctual degree, regardless of the structure, will contain either one or infinitely many non-pairwise functionally isomorphic elements. Okay. So if you look at omega with successor, right? Again, remember successor is the function that generates the next element in the chain. This is not functionally categorical, and pretty much the reason is pretty simple, because you can have punctual copies of this structure where you have non-standard elements that are floating around in different places. They will all get connected to the root, but they're kind of, right? If you think of the example with the computable graph, computable tree, it's the same situation here. You could have elements that are not immediately connected with the zero element, and to determine those, it will require an unbounded search. But anyway, this can be shown. This example can be used to show that every finitely generated structure has a dense PR degree structure. In fact, if you add rigid to the assumption, then not only is the PR degree structure dense, but it also embeds the countable Adamless Boolean algebra. Okay. So that was a discussion for finitely generated structure. So again, the result is every finitely generated structure has a dense PR degree structure. So the question is, what then can we say about structures which are not finitely generated? It turns out that the methods for those generally do not work, especially if your language is a relational one. And kind of the answer is the reason for that is kind of comes down to the fact that if your language is functional, then whether or not you succeed in doing certain tasks can be recognized in a pretty simple way. However, for relational structures, generally, this takes two quantifiers to recognize how you succeed, and this puts generally poses a big problem for showing denseness. Nevertheless, there is a structure which is essentially a graph, such that the PR degree structure is infinite but not dense. So this was kind of the first example of such a structure with a non-dense degree structure. So the example here is through a construction. Now, of course, it seems difficult to find such a phenomenon, right, of having non-dense in a naturally occurring structure. But subsequently, it turns out that, for instance, if you take the PR degree structure of the dense linear order, countable dense linear order, that itself is not dense, which gives rise to the title, the rationals are not dense. Well, this was the original title of the paper, but I think that's. Well, anyway, we changed it because. Well, I mean, if you have a title that says something like this, chances are that you get thrown out without. So anyway, we thrown this. We got rid of this, but okay. So the rationals are not dense, and so the main complexity of this comes from the fact that the rationals is highly homogeneous. So there is a usual strategy that kind of allows you to control how different copies of the structure that you build may behave, and these strategies simply don't work because of the fact that the underlying structure is extremely homogeneous, which means that there is no way for you to isolate different components and do the usual recursion theoretic trick to control. And there is also a second problem is that the isomorphic reductions are only built in the limit. So anyway, this was kind of surprising. But in contrast, if you look at the rationals, right, despite it not being dense, nevertheless the degree structure is nevertheless downward dense, in the sense that given any copy of the rationals, there is something below it. There's a second copy which is strictly slower than it. But the proof is not uniform, right? You can. If I give you a copy of the rationals, you can build a slower one, strictly slower one. But it's not uniform. You cannot do it uniformly. And in fact, you can. There are different facts now known about the rationals, the embeds, the diamond lattice, so on and so forth. Okay, so moving on to other linear orders, right? Nevertheless, this kind of copy switching can still be implemented for certain kinds of discrete linear orders. So, for example, if you take the integers as a linear order, in fact, if you take finitely many copies of the integers as a linear order, that is still that's dense. The PR degree structure is dense. On the other hand, if you have a discrete linear order with enough blocks, so this much is enough. If you take zeta plus zeta squared plus zeta cubed and so on, then it can be shown that this structure is not dense. Of course, there's a big gap in between, and that's one of the questions that we had. Okay, so just quickly, it seems that relational structures turns out to be difficult to classify, right? As we've seen. So if you look at other relational structures, for instance, if you are looking at equivalence relations, there is, however, a classification of exactly which computable equivalence relations have a dense functional structure, and that's exactly where you have these things called nice functions, G1 and G2, so that G1 is majorized by G2. And G1 kind of describes the character of the classes. Roughly speaking, the input to the nice function is the number of partitions, and the output G is the size of each partition. Of course, you're allowing the size to be infinity. So for instance, if you have infinitely many classes of size 2 and infinitely many classes of size 3, then that is not dense because you can take G1 to be 2 and G2 to be 3. If you have infinitely many classes, if you have infinitely many infinite classes, then it's also not dense because you can take G2 to be infinity. That majorizes any G1. And for example, if almost every class has the same finite size, then obviously you cannot separate G1 and G2. Then that is dense. Okay, so that's the situation for so far we have. Now, it turns out that there is a general criteria for dense for showing when a periodic degree structure is dense, and it turns out that if you look at the index set of all computable automorphisms of B, if that is effectively generated, that means that there is a so this is essentially this is an index set, and if there's a C set that generates the index set, sorry, a co-C set that generates the index set, then the structure is dense. But this is just a sufficient condition, and there is no, as far as I know, there's no sufficient and necessary condition. Okay, so let me just end off the first part with a few questions, which may or may not be interesting. So the first question is there a natural structure where the degree structure is so we know that there are structures where in fact natural structures, naturally occurring structures which degree structure is not dense, but in all of these examples the non-density was witnessed by an interval. Right? So we do not know if you can have a well, this is a slightly technical notion of a strong minimal cover. This seems to be difficult. And recall that there was this result about copies of the integers, right? So if you have finitely many copies, then that is dense. If you have enough copies, then that's not dense. And the question is what happens in between, right? So for example, if you just have omega copies of zeta, is that dense? This is one of the questions. In general, I think it's interesting to classify which linear orders, even amongst the discrete ones, which ones of those have dense PR degrees. Right, and this I think is also I believe another one of these where it seems difficult to get traction on. Now recall this, right? Having a single PR degree means again, what does it mean? It means that given any two copies, you have a primitive isomorphism one way and a different one going back. And the question is this always equivalent? Is this always enough for you to construct a single isomorphism where it and its inverse are both primitive recursive, right? Having F and G both ways, is it enough to have a single F whose inverse is also primitive recursive? You can think of this as the analog of Myhill's theorem for sets. Okay, we know for graphs this is true, and in almost every structure is true, but in general I believe the answer is not known. And also like which other partial orders can be realized. In general, this is also not known. Okay, any questions before I'm going to move on to the. Okay, so again, this is one example of reducibility that I'm going to discuss. So I'm going to discuss a few other ones. So they're all kind of loosely connected, but overall the whole idea is a goal of understanding of comparing algorithmic content through reductions. And here's another way that we might want to do this. So Josiah's talk from Wednesday, I think, right? So I think he kind of mentioned this. I'm a bit surprised that there have not been more talks on the wire reducibility, but since this is kind of the second one, so let me just again just remind you what the basic idea here is, right? So essentially, if you are looking at statements in reverse math, right? Which might be equivalent. Well, often the equivalence, or sometimes the equivalence, is witnessed kind of uniformly or computably, whatever that means. But sometimes you do have to resort to some tricks. And the idea is, how can we calibrate the complexity of such statements, which might be, again, equivalent, just in the usual sense, but perhaps not necessarily uniformly so, right? So if you look at pi1, 2 statements, then you can think of the statement as saying for every x there is a solution y to q, and you can think of q simply in the spirit of replacement axiom. You can think of q as being a function or general function that takes input x and sends it to the output y. Of course, the solution y is not necessarily unique. So it turns out that in computational analysis, there have already been tools to study these kinds of things. And so we're going to think of P and Q as, through passing to representations, we might as well assume that all problems are coded as elements of the Baire space, as functions for mapping elements of the Baire space to elements of the Baire space. And these are not necessarily total. This can be partial, multi-valued functions. And this allows us to define the reducibility on two problems, P and Q being functions, multi-functions, or we think of them as problems. Then we can say that problem P is reducible or simpler than problem Q, again in the same spirit of understanding how they relate. Basically, just means that if I want to solve P, then there is a way to compute, right, every instance of P into an instance of Q, so that solving that instance of Q allows you to compute a solution of P. And this is kind of legitimized through defining these Turing reductions that does the reductions each way, right? So you have a way of reducing or computing a solution of a P instance to a Q instance, and then you have a different way of computing Q solutions to P solutions so that everything lines up nicely. So that's basically the idea. And there is this notion of strong versus not strong, which I am currently, which I don't want to get into. And basically the relation here is that if P is reducible to Q, then usually this kind of says that you can have a uniform proof of Q implies P in the usual sense, ignoring induction, of course. Okay. Now this is all well and good. They've all been studied. There's a huge literature on the Weyl degrees, both in the global sense as well as classifying different kinds of problems. But what I just want to say is we can think of, right. So we've had this primitive recursive kind of to mean that you can solve a problem efficiently or in an online way. But what if you did this to the Weyl in the Weyl setting, but you insist, right? You mandate that the reductions have to be online. Okay, so you just replace the Turing operations with primitive recursive operations. Now I just want to say that the only property really that matters here is that the reductions phi and psi are total Turing operators. right? The fact that they are online in this particular case is not really that important. In some cases, it matters, but for most of the things that we looked at, it turns out that it's not really that important. Now, there is no. So first of all, this definition does not trivialize anything because there is a lack of compactness here, right? So if I fix an input n, then we know that phi n converges on all oracles, but because of the lack of compactness, you cannot compute everything in finite time. You can only compute it along a path that you pick. Each path you can take finite time to evaluate on input n, but of course in the entirety you cannot do it. Okay, so since this kind of reducibility now is finer, right, than the classical wire reducibility, it turns out that the choice of representation is often important when classically, if you look at wire reducibility, it's not that if you're not that loose with your representation, often it's not that important, but here's a bit finer, so the choice of representation is important. So for example, as a test case, if you just look at the most one of the most well understood combinatorial problems, which is Ramsey theorem for n tuples. I think this is pretty well known, but essentially what I want to say is that now you can represent, of course you can represent the homogeneous set in different, the solution homogeneous set in different ways, right? You could, for example, say that the solution is presented, the principal enumeration of the solution is presented. You could require for this as the output of the problem. You could require that the output of the problem to just give you any enumeration of an infinite homogeneous set, for example, not necessarily the principal one, but any enumeration, or the characteristic function, or just the color, right? It's all kinds of different things. And unexpectedly, well, it turns out that they're all different. But for pairs, there is no reduction amongst the first three. Just quickly, I think it's because for instance, right. So for essentially the reason is because for pairs, knowing the color isn't enough for you to make any judgment about the rest of the homogeneous set and vice versa. Okay. So anyway, there's this kind of picture is common in a talk on wire reducibilities. So in the spirit of things, I will put it here, but of course I'm not going to. Anyway, this is just an example, right? So one of these things that we could look at is what are some of the instances, for example, where having this primitive recursive reductions in fact refines the classical. So this is just a general question. I'm not going to really say anything about what we know and what we don't know, but it's just a suggestion of something that that people could look at. Okay, few minutes. Okay, so I have 4 more slides, I think. Okay, so for my third example, so I just want to quickly just mention this. I don't have many slides, but so. Right, coming back to Turing reducibility, right? It has been used to compare, again, right, as we mentioned, relative strength for total functions, for sets. Now, if for some reason you are interested in partial functions compared to total functions, well, how then can we say that one partial function is reducible to a different one? Well, it turns out that there have been different models. I think the best known one is perhaps Clini's model of relative partial computability. Now, it turns out that this is equivalent, right? So if you're thinking of the partial functions as being presented as graphs, then to say that the graph of one is enumeration reducible to the graph of the other is equivalent to this model. But this model is a form of non-deterministic Turing reduction, right? Because you obviously you have to deal with the fact where now on the oracle tape you have holes in the oracle tape, right, where the oracle may not give an output, and you can kind of avoid the bad path, right, but just by searching just in parallel, non-deterministically, right, many different paths, and it's okay if some of these paths ends up querying an empty cell. But as long as there is one path that does everything properly, then the whole thing converges, right? So this is known as non-deterministic Turing reducibility. And I think this is perhaps not as well known. We did not find many papers on this. Cecil apparently introduced a sequential version of this, so-called deterministic model. And the definition is what you think it is, right? For the sequential model, you require, in order for a computation to halt, you require every query to the oracle to be on a cell that is not empty, right? So once the computation attempts to query an undefined bit, then the thing diverges. So of course now there's two ways in which such a computation can diverge, right? It can diverge, maybe it does everything properly, but it just runs forever, or it makes finally many queries, and the last one is a bad cell. So now there's two possible divergence. And there is a slight modification to this model, which we call sub-Turing reduction, to say that F is sub-Turing reducible to G if there is a sequential Turing functional, so that F is a subset of phi G. So in other words, your machine is allowed to converge on more bits than F, right, as compared to being equal. This was Sasso's model. So why is this model? Why do people look at this model? Well, yes. So it has relationship with constructive mathematics, and it kind of reflects exactly the realizability subtoposes of the topos of effective objects. Okay. So anyway, that is the my third example. There are some questions, of course, here, but of course, I'm happy to discuss it if you're interested in this. But this was the kind of the third example of this thing. Okay, so yes, thank you. And